Star formation is one of the most fascinating and complex processes in the universe, representing the beginning of stellar life cycles that eventually lead to planetary systems and even the elements necessary for life. At the heart of this cosmic creation process lies gravity, the fundamental force that initiates and guides the formation of stars from vast clouds of interstellar gas and dust. The gravitational pull brings together diffuse matter into dense pockets that eventually become the shining beacons we see in our night sky. This report examines in detail how gravity drives the star formation process, from the initial collapse of interstellar clouds to the eventual birth of new stars. Gravity serves as the primary driver in star formation, causing the initial collapse of gas clouds, creating the conditions necessary for nuclear fusion, and ultimately determining the type and characteristics of the resulting star. Without gravity's persistent influence, the universe would be devoid of stars and the complex elements they create through fusion processes. Stars begin their formation journey in vast interstellar clouds, composed primarily of hydrogen and helium gas, with traces of heavier elements and cosmic dust. These clouds, known as nebulae, exist throughout galaxies and serve as the raw material from which stars are born. These molecular clouds are cold by cosmic standards, with temperatures typically ranging between 10 to 20 Kelvin, allowing gravity to overcome thermal pressure that would otherwise prevent collapse. The incredibly low temperatures and relatively high densities, compared to the surrounding interstellar medium, create the perfect conditions for gravity to begin its work. Even though these clouds would be considered a vacuum by Earth standards, their enormous size means they contain substantial mass, often thousands or millions of times the mass of our Sun. The initial state of these clouds is generally one of equilibrium, with the outward pressure from the gas particles balanced against the inward pull of gravity. This delicate balance can persist for extended periods, with clouds remaining in a stable state for millions of years. However, this equilibrium is easily disturbed. External influences such as shock waves from nearby supernovae explosions, spiral density waves in galaxies, or collision with other clouds can compress regions of a nebula, upsetting this equilibrium and triggering the gravitational collapse that leads to star formation. Sometimes even random fluctuations in density within the cloud can be sufficient to begin the process. When regions of a cloud become compressed, their density increases, strengthening the gravitational pull in those areas. The stability of interstellar clouds against gravitational collapse depends critically on the balance between gravitational potential energy and internal thermal energy. This relationship is expressed mathematically by the virial theorem, which states that for a cloud to maintain equilibrium, its gravitational potential energy must equal twice its internal thermal energy. When this balance exists, the cloud remains stable, neither expanding nor contracting. However, if the gravitational energy becomes dominant, the cloud will begin to collapse under its own weight. This fundamental principle underlies all star formation processes throughout the universe. The concept of Jeans instability, named after British physicist Sir James Jeans, represents a foundational principle in astrophysics that explains how and when gravitational collapse occurs in interstellar clouds. Jeans instability describes the critical point at which the internal gas pressure in a cloud region is insufficient to counterbalance the inward pull of gravity, leading to collapse. This concept answers the fundamental question: under what conditions will a cloud of gas begin to collapse to form stars? The Jeans instability serves as the theoretical framework that explains the very first step in star formation across the universe. When a region within a molecular cloud exceeds a certain mass for its temperature and density, gravity becomes the dominant force, overcoming the outward pressure that would otherwise keep the cloud dispersed. This critical mass threshold, known as the Jeans mass, depends directly on the temperature and density of the cloud. For typical molecular clouds in our galaxy, the Jeans mass often falls between 1,000 and 10,000 solar masses. This explains why star formation tends to occur in clusters rather than in isolation. A single large cloud typically fragments into multiple collapsing regions, each potentially forming one or more stars. The gene's mass is proportional to the temperature of the gas, raised to the power of 3 to 2, and inversely proportional to the square root of the density. In simpler terms, hotter clouds require more mass to collapse, while denser regions can collapse with less mass. This relationship explains why star formation preferentially occurs in the coldest, densest parts of molecular clouds. As a cloud begins to collapse and its density increases, its gene's mass actually decreases, making it easier for smaller regions within the cloud to begin their own collapse. This leads to the important process of fragmentation, where a single large cloud breaks into multiple smaller collapsing regions. The concept of gene's radius complements the gene's mass. It defines the critical size above which a region will become unstable to gravitational collapse. If a dense region within a molecular cloud exceeds its gene's radius, gravity will inevitably cause it to contract. This threshold represents the distance at which sound waves can no longer travel across the region fast enough to maintain pressure equilibrium against gravity's pull. When a region exceeds this critical size, gravity will always win the battle against pressure, initiating the formation of a protostar. Once the gene's instability threshold is crossed, the actual process of gravitational collapse begins. This marks the first definitive step towards star formation. During this initial phase, the collapsing cloud remains relatively transparent to its own radiation, allowing heat generated by the compression to escape efficiently. This means the collapse proceeds isothermally. The temperature remains nearly constant, despite the increasing density. The isothermal nature of the early collapse is crucial for star formation, as it allows the cloud to continue contracting without building up pressure that would halt the process. As the cloud collapses, its density increases dramatically, and with it, the strength of the gravitational field. This creates a self-reinforcing process. Stronger gravity leads to faster collapse, which increases density further, strengthening gravity even more. The free fall time, which represents how quickly collapse occurs, depends only on the density of the material, not its size. For typical molecular cloud cores, this free fall time might be around 100,000 years, extremely fast by astronomical standards. The collapse doesn't proceed uniformly throughout the cloud, but occurs more rapidly in the densest regions, creating a structure with a denser core surrounded by less dense outer layers. As the gravitational collapse continues, a fascinating physical principle comes into play: conservation of angular momentum. Most interstellar clouds have some initial rotation, however slow it might be. As the cloud contracts, this rotation must speed up, similar to how ice skaters spin faster when they pull in their arms. This accelerating rotation creates centrifugal forces that partially counteract gravity, particularly in the outer regions of the collapsing cloud. The result is that while the center of the cloud continues to collapse relatively unimpeded, the outer regions begin to flatten into a rotating disk. The conservation of angular momentum explains why most young stars are surrounded by protoplanetary disks, and why planetary systems, including our own solar system, tend to orbit in a single plane. Without this effect, stars might simply form as spherical objects without the flattened disks that eventually give rise to planets. The interaction between gravity and rotation thus sets the stage not just for star formation, but for the eventual formation of planetary systems as well. One of the most important aspects of gravitational collapse is that it rarely results in just a single star. Instead, the process of fragmentation occurs, where the collapsing cloud breaks into multiple smaller cores that form individual stars or binary multiple star systems. This fragmentation happens because as the overall cloud collapses and its density increases, the gene's mass decreases proportionally. This means smaller and smaller regions within the cloud become susceptible to their own gravitational collapse. What might have started as a single large unstable region can eventually fragment into dozens or hundreds of smaller collapsing cores. The fragmentation process explains several observed features of star formation. First, it explains why stars typically form in clusters rather than in isolation. Second, it helps explain the distribution of stellar masses we observe, from lightweight dwarf stars to massive giants. The precise way a cloud fragments depends on factors like its initial density distribution, rotation, magnetic fields, and turbulence. These factors create local density enhancements that serve as seeds for fragmentation. In regions with more turbulence or stronger magnetic fields, fragmentation can be either enhanced or suppressed, affecting the final distribution of stellar masses. While gravity is the primary driver of star formation, turbulence and magnetic fields play critical roles in modulating the fragmentation process. Turbulence creates local density fluctuations within the cloud that can either promote or inhibit collapse in different regions. Strong turbulence tends to create more fragmentation, resulting in a larger number of lower mass stars. Magnetic fields, on the other hand, provide pressure support against gravity and can slow the collapse process or prevent it altogether in some regions. The complex interplay between gravity, turbulence, and magnetic fields determines the efficiency of star formation and the distribution of stellar masses within a forming cluster. The importance of these factors varies depending on the environment. In regions with strong external compression, such as near supernova remnants or in colliding galaxies, turbulence might dominate, leading to rapid and efficient star formation. In more quiescent regions, magnetic fields might play a larger role in regulating the collapse. This explains why star formation rates and efficiencies vary widely across different regions of our galaxy and in different types of galaxies throughout the universe. As gravitational collapse continues in a particular fragment of the cloud, the central region becomes increasingly dense and begins to form a distinct object known as a protostar. A protostar is essentially a densely packed sphere of gas that continues to accumulate material from its surrounding envelope. At this stage, the protostar is not yet hot enough to initiate nuclear fusion, the process that defines a true star. Instead, its luminosity comes exclusively from the conversion of gravitational potential energy to heat as material falls inward. As gravity compresses the gas, the atoms and molecules move more rapidly, raising the temperature at the center of the forming star. The protostar stage represents a critical transition in the star formation process. The central object is now distinct from its surroundings, though it continues to grow by accreting material from the collapsing cloud. The temperature at the center of the protostar rises steadily as gravity continues to compress the gas. This heating is a direct consequence of the gravitational collapse. As gas falls inward, gravitational potential energy is converted to kinetic energy and then to heat through collisions between particles. The protostar remains relatively cool and large compared to a main sequence star, typically spanning several astronomical units in radius. During the protostar phase, the growing stellar embryo continues to accrete material from its surroundings through the force of gravity. This accretion process isn't uniform, but tends to occur through a flattened disk that forms around the protostar due to conservation of angular momentum. The gravitational energy released as material falls onto the protostar's surface generates significant luminosity, often much greater than the protostar will have once it becomes a main sequence star. This accretion luminosity can make protostars difficult to observe directly, as they are typically shrouded in the dust and gas from which they're forming. The gravitational collapse also leads to another important phenomenon: the generation of protostellar winds and jets. As material spirals inward through the accretion disk, magnetic fields channel some of it into powerful, collimated outflows perpendicular to the disk. These bipolar jets can extend for light years into space and play a crucial role in removing angular momentum from the system, allowing accretion to continue. The jets also interact with the surrounding cloud material, potentially triggering additional star formation or dispersing gas that might otherwise form stars. This represents another way gravity indirectly shapes the star formation process, by driving accretion that powers these influential outflows.